Good afternoon, everyone. And the first topic I'm going to take up is that of combined stress. And this is a very common situation in machine design. It's where I have, at a given point, a given stress cube, more than one type of stress occurring on the cube. So this is an example out of the text, so you don't have to do a lot of scribbling. You can refer to this in the text. I cut the number off, so I don't remember what number it is, but it's in the chapter. So here's a picture of a rod that's buried in the wall in some fashion, and at the end of it there is another piece of metal on it, and they're fastened together in some unspecified way here, so they can't move with respect to one another. Then a load is hung on this arm out some distance A from the center of the rod, and the force is also L units from the end, from the wall. So the tube is L long and the arm is A long. And I have this force, a single force, downward, presumably a weight hung on there. And if we do some analysis of that beam, we'll find that it has a loading diagram that looks like this. It's a cantilever beam. So the wall is at 0 and 6 is the value of L, apparently. L is 6 inches. So at the wall we have a reaction force R1, and we can calculate the value of that from some of the forces equals 0, some of the moments equals 0, right, to get the moment and the reaction force. And of course there's also a moment at that point, which I don't show in this diagram because this is a force diagram, not the moment diagram. The moment diagram will come up in a minute. So if I integrate this, I'm sorry, there's my force F out at the end. I didn't mention that. So there are the two forces shown. R1 is, of course, equal and opposite direction to F, right? From some of the forces equals 0. And if I draw the shear diagram for that beam, I have a value of R1 at the outset, and I see nothing else as I walk across the beam. The way I used to tell students to figure this out years ago, before we had computers, I would say, imagine you're walking backwards across the beam. I want to draw the shear diagram. You're walking backwards across the beam, and you're going to record in your little pad every force that you see as you walk backwards, okay? So I take one step back, and I see R1. And so I still see R1, 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 R1. And as I step off the beam and go, I see F. And scribble that down before I splat on the pavement, okay? So what you're doing is recording the forces that exist across the beam. So initially I have an R1 from your side, it goes up. It stays the same until at the very end I have F1 and brings it back to 0. Okay? So it has to close. Now it not obvious that it closes because this went from 0 to 1 and then it stayed at 1 and came back down again. So these diagrams always have to start and end at the same place. Is that clear? So the moment diagram is the integration of that. So again, I could walk across the beam. Now I'm walking across this diagram. I'm recording the area that I see, which of course is the integral, right? And by baby steps, I see a little bit more area. So I'm going to get this. Actually, I have to walk the other way, come to think of it. I got smart. I decided I'm not going to fall off the beam the second time. I'm going to walk this way this time, so I walk toward the wall. The difference has to do with the sign conventions, which are silly because the shear convention's opposite to the moment. So an upward, a positive shear gives me a negative moment because of the funny sign conventions. So this time I got smart and I'm walking this way. So I see a little bit of area, then a little more, a little more, a little more, a little more. And this is the value of the areas, because when I finally get to the wall, I've got all the area accumulated and got my biggest moment at the wall, right? So that's essentially all I need to analyze the beam conditions, because I need the shear and the moment. But I also have a torque. And that torque exists all along the tube because I'm out at the open end of the tube out at L and putting that force on with a lever arm, which is that distance A, and that creates a torque in the tube. Now, of course, the wall is resisting that torque with another torque of the opposite direction, right? So much like the V diagram, it looks just the same except the numbers are different. I have, coming in from the end, from the right-hand end here, I have an applied torque of 8,000 inch-pounds, I guess, because I'm 8 inches out and I've got 1,000 pounds. And that's the same all the way across until I get to the wall, and then there is a counter torque that gets me back to 0. So those are the four loading diagrams of this system. And what I want you to do right now, take a couple of minutes, chat with your neighbors on either side of you or on one side of you. Take out a piece of paper if you need it, and I want you to in a couple of minutes, tell me what kind of stresses are we going to have at A and B with that loading. That's two separate questions. What kind of stresses do I have at A, and what kind of stresses do I have at B? So chat about this for a minute or two. Well, I get a glass of water. I'll be right back. Who has some ideas? What about A? What's happening at A? Go ahead.
At A, I think the normal would be maximum, and there'd be a torsional stress there.
If you didn't hear what he said he thinks at A, the normal stress will be maximal. In what direction would you think it would be in? Positive X direction, I'd agree with that. And you also said something about torsional shear would be at A. Everyone agree with that? That's correct. Because you have, as we discussed the other day, a distribution from the top to the bottom of the beam with maximum bending stress on the top and the bottom, and it could be either plus or minus depending on which way you're loading it. Being a cantilever beam, I'm pulling down on the end, I'm stretching the top surface. This is my beam right here. So if my right hand is the wall and this is the load, I'm stretching the top surface and compressing the bottom surface, so I'd expect to have maximum normal stress here, maximum compressive down here at some other point, right? And then the twist, we're going like that, and the torque at the end of the beam is resisted by a torque in the wall, and that's going to put a torsional stress, which is shear, which is uniform, is not uniform, but increases with the radius, but it's all the way around the circle, right? That's good. So what about B? Yes?
You will have the same magnitude and proportional stress at A, but in 90 degree direction.
Yep. What else? Anything else there? He's saying that we have torsional stress at B, same magnitude as at A, but 90 degrees from the way it was at A, because it's around the corner. Yep.
If B is at the center of
Neutral axis, yeah.
it would be zero.
Normal stress is 0, that's correct. Anything else happening at B? Yeah. Did I see a hand up? Yeah, what else is happening at B? The transverse shear stress. Remember the pad of paper? With the piece of paper sliding on one another? And that's maximum at the neutral axis, which is, if you have a uniform geometry like a circle, neutral axis is in the middle. If the geometry is not uniform, it's someplace else. So the neutral axis is in the middle, and therefore at B I have two shear stresses. I have a torsional shear, and I also have a shear due to bending or transverse shear. Both terms are used. So we have combined bending and torsion at A. So I now want to find the magnitudes of these and put them together in some fashion so I can figure out what's going on. So if it's bending stress, it's MC over I, and the moment here is F times L. Is that correct? Yeah, F times L. And put the numbers in, I get 18,000 and change PSI. And that distributes, as we just discussed, as you see here, with it being 0 at the neutral axis, maximally tension at one side, maximally compressive at the other. In this case, the tension's on the top. So I probably would also want to look at point C, which is the bottom, because that's going to have some other stuff going on too. The tau xz Notice the labels, my z-axis is this way and my x is this way, so it's acting on the x face in the z direction. That makes sense? Imagine a bologna slice there right at the wall, and I'm, shearing that bologna slice against this neighboring bologna slice, and at that top point it's going to be shearing horizontally. Yeah, and that comes out to be 12,000 and change. And I try to show this as a fan that's really continuously all the way around, the same value all around the outside surface, tapering to 0 toward the center of the circle. So now I have, for point A, I now have my applied stress state, which is those two stresses. And this is where the principal stress comes in. That's how I combine them, okay? Because the principal stress equation has both normal and shear components. It's a two-dimensional case because I don't have a third dimension in terms of the stresses. So I put it into the formula for maximum shear and sigma 1, 2, and 3 based on the equations we derived earlier. So I get a maximum shear of 15,000 psi, and I get a sigma 1 of 24 and a sigma 3 of negative 6,000. And being a 2D stress case, the other guy is 0, sigma 2 in this case. So you could draw a Mohr's circle for that, which is just an alternate way of solving the problem. But with a computer available, it's easiest to calculate using the formulas. Everyone clear on how I got those numbers? Before I move to point B. Any questions on where they're coming from? So if I'm worried about breakage now, I'm going to compare the normal principal stress, the biggest of the set of numbers, to some strength parameter, which we'll get to later. And likewise, I'll compare the maximum shear to a shear strength parameter, and they're different. The same material will have a different strength in shear than in tension. One may be bigger than the other in either direction, depending on the material. We'll deal with that later. So now I'm at point B, and we've decided we have two shears there. So that makes our life a bit easier. We already calculated one of them. That was the TR over J, right? That's my so-called torsional shear. And you already pointed out it's the same value at B as A, just the direction is different. And I now need this tau bending, so-called, which for a circular section we find is 4/3 times the value of V divided by the area of the cross-section. That turns out to be small compared to the other. And that should not be surprising. There's a rule of thumb that you may have been told in ES 2502 that the shear due to bending, or transverse shear, it's more properly called transverse shear, but a purist would say it's not really due to the bending, it's due to the... Anyway, I call it by either name. So that shear that's from all the pieces of paper trying to skid on one another will tend to be small in a long beam. Why is that? Well, if I have the same load, whatever this was, 1,000 pounds, and I double the length of the beam, does the shear diagram change in magnitude? Still 1,000 pounds. It goes twice as far, but the number doesn't get any bigger. Does the moment get bigger? Oh yeah, it doubles, right? So if the beam is long, the moment dwarfs the shear. But as I get shorter and shorter and shorter, at some point, they're not going to be so different. And the rule of thumb is if the length of the beam is 10 or more times the depth, then we consider the shear to be small and sometimes don't bother to calculate it. But if the ratio of length to depth of the beam is less than 10, then you ought to be looking at that transverse shear, because it could be big enough to give you a problem. So this is a relatively short beam, because I've already forgotten what diameter I had there. I think I gave the diameter of that thing. I must have. What is it? 1.5 inches, and I'm 6 inches long, so that's less than my 10 to 1, I think. So this is a case where the shear due to bending could be a problem. So we do want to take care of it. So back to where I just left off. So it is still not very big compared to the other guy, because I've got a long moment arm on that place where I put the F. That gives me a big torque. So that's tending to dwarf that. But bending stress, of course, is 0 here. So these are on the same face, so I can just add them together and I get about 13,000 psi. So this thing could fail at either point depending upon which numbers happen to turn out bigger. So the moral of that story is that when you look at a system like this, a very simple system, you have to use your understanding of how loads are distributed and how stresses distribute within the cross sections to decide where am I going to spend my energy calculating. I don't have all the time in the world to calculate a zillion points on this thing. I've got to focus in on where I think the real problem is. Okay? So that's typically going to be where the moments are large and where the shear values are large. That's my position along the beam in this example. And the other issue is, where am I in the cross section? Well, bending, I'm out at the outside. Torque, I'm out at the outside. Shear due to bending or transverse shear, I'm at the midline, at the neutral axis. Anybody have any questions so far on that? So here I'm drawing little stress cubes to show what's happening here at the two different points, A and B. And I say here that point A has the larger principal stress, but the relative values of applied torque and moment determine which of these 2 points will have the higher principal stress. In other words, if I made the arm longer where I'm applying the torque, then that could become dominant, right? So the geometry of the system will determine which point is the most in trouble. Therefore, I have to check both. Before we change topics, everyone okay with this? This is a very, very important concept to understand because you're going to run into it over and over and again. You have to consider where in the physical system are the loads the greatest. Cantilever, moments at worst at the root, right? If it's simple supported, the moment's worst someplace in between the two supports. You've got to figure that out. And then cross-section, where the stress is the worst. Okay, different topic, stress concentration. You should have been introduced to this in your earlier course as well, but a rough definition of it is whenever the geometry changes, especially abruptly, there's going to be a concentration of stress, which means that you will have larger values than is apparent from the standard formulas. And we call that a stress concentration. It's also sometimes called a stress riser. The term stress riser usually refers to the physical geometry on the part. Oh, there's a stress riser, because it's going to concentrate the stress there, right? Now, it's important to understand this is not an artifact. This is not some funny business. It's really there. There really is higher stress there, and you can see that if you do a finite element analysis. But when we're doing hand calculations, or I call these classic calculations, using classic formulas, whether I use a computer or not, as opposed to finite element methods, I'm limited by my formulas to calculating for the general case. You know, in a cross-section, it's worse at the outside surface and so forth, in bending and also in torsion. But if I have some kind of a notch there, then I'm going to have more than that formula tells me. So I'm going to have to take care of that in a separate calculation. And some examples of things that cause this are holes, keyways, notches, any sudden change in dimension or shape. Now, you can actually see the stress concentrations if you do certain tests on parts. Now, back in the days before there were computers, the only way we could really see the stresses was to do something called photoelasticity, a really clever technique that someone came up with, like, I think back in the early 1900s, but I'd have to check to see when it first came in. But it only requires photography and a polarized light source. And those have been known for a long, long time, both of those things, right? So this shows the actual part, and it's got this would be a notch. There's a change in contour, also a notch. The term notch is used universally to describe any sudden change in contour. So even though that's not a full notch, as you might think of it, it's referred to as a notch, okay? So that's a piece of something or other, and it's going to get loaded in bending. You can see the stress distribution across here. So there's a moment over here being applied. And this photograph was made by taking this geometry and actually cutting it out of a piece of material of the appropriate thickness. Actually, the thickness is not critical for this experiment. Made of a certain plastic. In the old days, they used something whose name I forget. The modern method is to use Lexan. Lexan works well. It needs to be a transparent plastic. And of course, plastic is not very strong, so without an awful lot of force, I can put some stress into the thing. And so what you do is you set that piece of plastic up in a fixture, which you have to make, so you can load it the way the part is really loaded, and then you photograph the loaded part with polarized light. And the polarization causes these bands to show, and those bands represent changes in stress. So they're actually the stress fields in the part. So where the bands are close together, the stress is higher, and where the bands are further apart, the stress is lower. So notice how the bands get closer together right around these notches, and they get further apart in the middle of the part and over here, and then around this notch they're quite concentrated, thus telling you qualitatively that you have stress concentration. So techniques were developed way, way back to count or measure the distance between the bands and use that to impute some values of stress. So we now need to be careful in our language when we calculate something from MC over I, MD over I, whatever you want to call that distance, or TR over J, which is our torsional shear stress. We're calculating what is properly called the nominal stress, from which it may increase due to stress concentration if there is any. So what we need to do is determine something called a stress concentration factor, typically given the letter capital K and a subscript T or TS, which is the S stands for shear. So it turns out that these values will be different depending on how you load the part for the same notch. So you'll find separate values for the two different cases. The T indicates that this is what's called a geometric stress concentration, due strictly to the geometry of the part. And as you might expect, if the notch is sharper, this number gets bigger. If the notch is gentle, it gets smaller. If there's no notch, it's essentially 1. It's a multiplier by the stress, the nominal stress, that will tend to increase the stress. So it's a number between 1 and something. There have been some theoretical studies done for certain neat geometries. A hole in a plate. You can actually calculate with closed form equations what the stress concentration will be if you have a hole in what they refer to as a semi-infinite plate. All that means is there's a little hole and a lot of plate, so that away from the plate nothing's happening that's affected by the hole. So here it shows a plate in tension, and there's a hole actually done as an ellipse because we can change the geometry of the hole by changing the ratio of A to C, the two half dimensions you see there, C over A in the plot to the right. So this curve is a calculation based on theory of elasticity that shows what the stress concentration will be as a function of that ratio C over A. Now, of course, when C is equal to A, I have a circular hole, right? So that would be 1. And if you look at 1, which isn't on the chart, but halfway between 0 and 2, and you run your eye up, you'll see it's exactly 3.0. So a circular hole in a semi-infinite plate has a stress concentration of 3. So whatever the nominal stress is across that plate, which I would find by taking that force P and the area through the hole, now I could either, subtract the area of the hole to get a real accurate answer, or I could simply take the area of the whole plate, and I would have a small difference. Again, depending on how big the plate, how wide the plate is, and how big the hole is, it could make a significant or an insignificant difference whether I leave the hole's area out. Typically, you leave it out. That is, you don't bother subtracting it. But in the case of a circular hole, I would have to take that P over A stress, which is a normal stress, and triple it to get an indication of what's happening at the hole. That can make a big difference. If you didn't do that and use a safety factor of 2, what's your safety factor going to really be? It fails at 1 and below. Okay? So you've got to take this into account. And of course, if I get the thing more and more elliptical so that C gets smaller and smaller with respect to A, this goes off to infinity. So if that's a sharp crack, I have potentially infinite stress. And of course the material can't stand that. So what's it going to do? It's going to yield. If it can yield, it'll yield. And it'll yield if it's ductile. If it's brittle, it's all over, it breaks. But if it can yield, what it'll do is yield and open the crack up and make the radius something other than 0 until it reaches equilibrium. And if in the process of doing that, it doesn't crack all the way across, it still holds together. And it reduces the concentration by changing its geometry by yielding. Now, how do we determine what these numbers are? Well, a lot of work was done on this by a fellow named Peterson. And that was published by Mr. Peterson. And this is the newer version of the book. It's called Peterson's Stress Concentration Factors by a couple of guys named, or actually a man and a woman named Pilkey. So inside this book, which is a Bible that we already refer to, are charts. And these charts are for various situations, you know, a hole in a plate, a notch in a round bar, under this loading, that loading, the other loading. And so you go through this and pick them out. So my book, as well as every other book on the subject, has permissioned a set of these out of Peterson. And in one of my appendices, you will see pictures like this. Now, I just picked one of them for example. This is a bar, rectangular cross-sectional bar in bending moment, loading, and it has a change in section from little d to big D. And the curves are plotted, much like the ones you saw for the hole in the plate here, as a function of r over d. Well, r is the radius of the notch, and little d is the smaller of the two dimensions. And kt over here, you'll notice, goes from 1 to 4-ish. And the other parameter is the ratio d over d. In other words, how severe is the notch, as well as what's the tightness of the radius. And that shows up as a family of curves, 3, 2, etc., for that ratio. And those are all shown as you see. Now, if you go to Peterson's book or other books on the same topic as mine, you will find just those charts. And you're expected to go, and they're on nice crosshatch paper. So you go in there and you pick off a number by reading the chart, interpolate between the lines and all that stuff, and get an approximate value. I thought that was kind of clumsy, so what I did was I did just what I said. I went and picked off data, but I used the data to create functions. And I found a function that fit most of them. It's an exponential. So the value of a as a coefficient times r over d raised to the b power will give me every one of those curves, provided I use this a and b that you see in the chart, which corresponds to these factors up here. So I've gone Peterson a step better. It took me a long time to do this because I did it for a whole bunch of these things. And I generated functions. So I can call those on the fly from inside my computer program. And I can hand it the big D, the little d, and the r, and get back the k sub t on the fly, which is a lot less work than opening up the book and poking around in the back to get my number, right? So these data are all on the CD in your book as TK files, and I think they may also be there as MathCAD and the others. Other people did the MathCAD, the MATLAB, the Excel, and the whatevers for that book. Publisher hired them to do it. I did the TK stuff, so I'm certain what's there in TK. Yes, sir.
So there's a stress concentration at the radius?
Yes.
So when you're...
Sharp corners are your enemy in this business.
So
you don't want sharp corners because the radius is 0.
okay. So if that was a 90-degree turn rather than a radius,
It would go to infinity.
it would be bigger?
Yeah, like infinity.
Okay.
Like your hole, when you get that ellipse down to a crack,
Yeah.
so that the vertical dimension is 0 and the horizontal is something, it's a crack. And that theoretical stress concentration goes to infinity. And the same is potentially true here. As an aside, we'll get to failure analysis pretty quick, but given your question, it's worth tossing out a little preview here. All fatigue failures start at a crack. And all materials have cracks from the factory. They may be so small you can't see them, but they're there. And microscopic cracks are sufficient to start the process, which is called crack growth. And when it gets big enough, the thing fails. And there are ways, as we will discover in the next few weeks, that we can design to avoid those for a long enough time, like billions of cycles, so this thing is probably in the dump anyway. Okay? But everything starts at a crack. So here's how, this is right to your point. You're ahead of me by about one slide, so that's good. What I'm showing here is a concept called force flow. It's kind of neat. If you think of the forces going through the part as sort of like a fluid problem, right? They're flowing through the part. Then let them come from the left to the right in this example. And as they get to that little drop in diameter, this is a round thing presumably, they have to all get crowded around to get around the corner. So they all get smushed together closer. That's the stress concentration we're talking about. So to the degree that I disrupt the flow of the force through the thing, I'm going to create stress concentrations. The fluid analogy is apt because I'm sure you intuitively understand that if I want water to flow through a pipe smoothly, I don't want to have sudden changes of pipe diameter, right? That's going to cause a backup and a problem. A nice gentle transition down would be much better, right? Same concept. So some of the things we can do to improve this is, as you just observed, put a radius in there, right? Now, that's your first line of defense. In some cases, you might need that sharp corner for another purpose. For example, maybe I want to put a bearing right up against that thing. And the bearing, that purpose of that change in section is to provide a flange against which the bearing will stop, right? A shoulder. So if I do nothing else, I'm going to have that problem that I show in the first picture. But there are some tricks I could do to avoid that. For example, if I put a radius of this sort in there, this little nubbin here is doing the job of holding the bearing where I want it, and it has hardly any stress in it because the stress just went around the corner and down through there. Okay? In similar fashion, I could take it out of the backside, and I'm giving it a smoother path through, or I could add another part, which is essentially a washer, and I put a chamfer on the washer, and I put in the radius that I want, and that chamfer straddles the radius. And there's many other varieties of things I can do. The bottom line here, the point of it all is, don't have sharp corners. They're going to give you trouble, okay? You want to have smooth changes in contour every place you have to have such changes in contour. This shows a crimping tool, which is used to crimp a little fitting on the end of a wire. You've probably used those things. So it just smushes the fitting onto the wire, and it takes a fair bit of force. This particular one developed 2,000 pounds of force at that crimp. And as such, you get some stress concentrations. If you do a stress analysis of this part, you will see the stress concentration show up in the stress plot, analogous to that photoelasticity. So nowadays, they don't do photoelasticity anymore because you can do the same thing with finite element, and it's a lot less work. But the mesh has to be very fine around these holes, otherwise you won't see it. But you can see the concentration right where the crimp is occurring right there, and concentration down here on the bottom of this curved beam. That's in tension, right? And pull this out. This is in bending. And there's a change in contour there, even though it's rather generous. So stress concentrations are real. They're not an artifact, not a fiction. Is everyone comfortable with the concept of stress concentration? We're going to see it again and again before we're done. Okay, different topic altogether. A column is defined as something that is relatively long and slender and is expected to hold something up. So it's in compression. And you've seen these. They're holding up our buildings, right? Holding up the bridges. Maybe holding up your house. There's a problem with columns that's quite dramatic. Okay, I have here another noodle, longer than the other, made of the same material. And I'm going to use it, in this case, as a column. So a column is used to hold something up. And if the column is relatively long versus its diameter or its dimension, then it's called a slender column. And we have something called a slenderness ratio that we can calculate to determine whether it is or is not such an animal. And the problem with this is when it fails suddenly and catastrophically. Now I'm going to start putting a load with my hand on the top of this column. You can see it shaking slightly. And when that load exceeds a certain value, it suddenly bends and gives. And what's happening is, as I push down on it, it's deflecting slightly. And as it deflects, the load which is passing through the center line of the column is now offset from the line from my hand to the floor. And that gives a moment arm that increases the bending moment, and that's a case of positive feedback. So as that deflection increases, it gets to a critical point where the bending moment increases without limit, and the thing will go to failure. This is why bridges fall down in some cases and why buildings collapse. So we have to be careful when we design a column to take into account these issues to make sure it's safe. And I'll show you that in some slides. So a very dangerous form of failure that we obviously have to guard against. Well defined mathematically, so let's talk about that. So one of the factors that determines whether the column is prone to buckling or not is something called the slenderness ratio. It means just what it says. Is this slender like this noodle or fat like me? You can't buckle me. No, not a prayer. So it's defined as the, as you see there, the length of the column divided by something called little k, which you may recall is the radius of gyration of the cross section. It's related to the area moment of inertia. It's actually the square root of I over A. Okay? So we can calculate the area moment of inertia of that thing. Cross-sectional area moment of inertia, each is fourth, our millimeters fourth would be the units. And we can divide it by the L and find out what that value is. That's going to tell us something about how this column can be expected to behave. So if that ratio is less than 10, it's a ratio, so there's no units to that, then we expect this will not buckle. Instead, it will just smush. It'll crush. So I will make a coin out of it if I push hard enough, long enough. Okay? It's just going to get fatter and thinner, top to bottom. Shorter and shorter, I should say. Fatter and shorter. And I can then go about the calculation very simply, P over A, just as you would for tension. If I'm greater than 10, then I have one of two possible cases, which are referred to as intermediate and long columns. In my experience in the machine design business, I've very rarely met a truly long column. I think civil engineers work with them all the time because they got, bridges way up there, and it's a very tall column. So that's going to be a really long column. But in machinery, they're more often in the intermediate range. But it's easy to figure out. But now, our safety is going to be defined by something called critical unit load, which is P critical, which is a force, divided by A. It looks like the same formula, doesn't it? But it's not stress. It looks like stress, but it's not. It's a unit force, a force per unit area. Same units as stress, but not quite the same thing. So, by the way, all these formulas are based on the assumption that the loads are concentric, not offset, right? Because clearly if I start out holding this on the edge of the table like that, and I push on this side over here, I've already got a bending moment, right? There's a couple there. So I'm sort of goosing it. I'm going to go quicker to failure that way than if I'm right in line, right? So these formulas are assuming you're perfectly in line. I'm not going to get to it in the lecture, but in the book I give you the approach when you know that they're not in line, called the secant formula. That's still a third approach that I'm not going to cover here today. So the bending moment here is just as it would be anywhere else, P over Y. Y is the offset. And notice that when it starts to buckle, the center or belly of the column is set off to one side, like so. What does that do to the moment? Increases. More moment means what? More deflection, which means more moment, which means more deflection, which means more moment, which is why it goes suddenly to failure. It's a positive feedback situation. So once you start it, there's no stopping it. So if you want to fail the column, give it a good smart smack in the middle sideways, and it probably will come right down on your head. Because you'll start that self-booting process of positive feedback. For small deflections, we can write that differential equation, and we better not get big deflections with this, or we're going to run out of town on a rail. So there's the differential equation that governs it. This is a derivation that's in the book, and that differential equation has this well-known solution, a sine and a cosine term. I'm going to go through this quickly because it's in the book, and you can study it at your leisure. We have two constants of integration. We have to figure out what those are, and they depend upon something called end conditions. Now, the end conditions are the way that the ends of the column are fastened, which is sensible enough. So the reference on which all is based is the rounded. So that would also be the same for pinned, by the way. If I put a pin through this and a pin through this, the pin is a rounded thing, so that's essentially the same as rounded. But if I had a round end here and a round end there, I got point contact on both ends theoretically, right? I don't recommend that as a good way to do it, but that's the reference, okay? So here's my rounded case. I could do pinned. I could do fixed, bury it in the ground. This is your flagpole, right? Free at the top. I could do fixed and guide the pin the top, or fixed. And there's some other possibility. I could guide the top and fix the bottom, and so forth. Each of those will have a different shape, as is shown here. Actually, these two are the same animal, but this clearly is different, and this is different again, this is different again. So they will fail at a different load. So how do we handle that? Well, first of all, we find the equations for the pin-pin condition. That's straightforward. And we find these factors, C1 and C2, and from those we develop a formula that says the square root of the force divided by EI. E is the modulus of elasticity of the column. I is the area moment of inertia of the cross-section. L is the length. And there's multiple solutions to this thing because I can have n times pi, where n goes 1, 2, 3. So there's multiple conditions under which it'll fail. I don't care about any but the first. If it fails then, it's all over. Right? I'll never get to the others. So we want n equals 1. If you put n equal to 1, I get this expression right here, and this is referred to as the Euler equation for long columns. I'll define in a minute what makes it a long as opposed to an intermediate. I is ak squared, where k is the radius of gyration, and SR is, as you saw earlier, L over K. So this is what's called the critical load per unit area, and the boundary conditions are, as you saw, pinned, or rounded. So that's sort of the standard. Euler was around a long time ago, right? You've seen that name before. Centuries ago, he figured this out. So how do we account for these other cases where I have it, flagpole on the ground, free end, or whatever? Well, the easiest way to do that is to apply a factor to the length of the column and pretend the column is either longer or shorter. Actually, most of them all are going to be longer, I think. No, a few are shorter. So the L in that formula up above refers to the, well, I guess I've changed the picture. It's now L effective, and the L was derived for the pin-pin condition. And that's then worth 1L. So if I have either rounded or pin-pinned, my effective length is 1L. If I have a fixed free, that's my flagpole. That's effectively a twice as long pin-to-pin column. In other words, it's half as strong, right? If I bury that in the ground and sit on the thing up here, it's going to fail with half the load if it's the same length. So it's as if I had twice as long a pin-pin column. You see what's happening here? So we're going to jack the L up in the equation, which is going to give me a weaker column, right? And for the fixed free, and for the fixed pinned, it's less than because I've pinned the other end and fixed this end. And a fixed moment joint is stronger than a pin joint. So the slope of that coming off the bottom is 0. And it's half if it's fixed, because now I've fixed both ends in concrete or whatever, and they can't wiggle, okay? So it goes down to 0.5. These are the theoretical numbers. American Institute of Steel Construction, which is what that stands for, which is the, the outfit that worries about big buildings and bridges, they suggest that these numbers are more conservative and better to use than the other guys. And a real conservative value would be to do this. So you pay your money and take your choice. I would use one of the two right-hand columns here in a real situation. Is everyone clear on what's happening there? We're going to fudge the length of the column based on the end conditions and use the same equation in all cases. Okay, now what about this intermediate business? Well, the plot on the left shows what's called the Euler line, this red line right here. And so if you plot that versus slenderness ratio of the column and look at whether or not the columns, if you do a bunch of tests, whether they fail or they don't, and the failure, of course, is going to be based on the compressive strength of the material, is it not? We're putting it in compression. So we've got to get the SYC, that's the yield and compression in here. So that's what you see on the vertical axis. So as it turns out, if you make columns that are to the right of this red line, you would expect them to fail, and to the left of the red line within this envelope, you expect them to be safe. And you can apply then a safety factor in addition. So that red line is the line along which they break, okay, or buckle. And so you would not want to get too close to that. You'd pull back by some safety factor. But a lot of tests were done, and it turned out that a lot of columns failed up in this region that you see depicted, whoops, by this black line and the Euler curve. This horizontal line is the short column line. That's where you have gone beyond the yield strength and it just crushes. So failures occur in this so-called empirical failure zone. So when that was discovered, a guy named Johnson said, well, we don't want to go there because we know it fails from testing. So I'm going to create a curve that stays away from there. So all the failures that occurred in experiments were outside of this line, and he chose to create a parabola that has zero slope and goes through the yield strength of the material on the axis and is tangent to the Euler line at a value halfway between 0 and the yield strength of the material. So that point in the middle is SYC over 2. So if you plug those numbers in as boundary conditions for a parabola and solve it, you get the equation you see down here. So the Johnson line, so-called, is for P critical is equal to the area times the, now notice we have now the yield strength, which was not in the Euler equation. Notice the Euler equation only had Young's modulus. Did not care how strong the material was, only how stiff it is. So the yield stress does not occur in Euler's equation at all, but it does in Johnson's, because we're now getting into this other problem of some of the Euler, the good Eulers are not good. They're failing up in this neat neck of the woods here. So we have to decide which of these curves we want to use. Well, the test is to take, you know what your strength, I should say, of the material is for whatever you're using. And you take half of that and you apply that value to the, to find out what is the slenderness ratio at point D, which is where that curve intersects the Euler line. And you then ask yourself, is my slenderness ratio to the left or the right of that value? If it's to the left, I use the Johnson line. To the right, use the Euler line. As I said earlier, most of the columns I've encountered in machinery, which tend to be relatively short, have been to the left of the, that point D, and are in this intermediate category. I think buildings and bridges, you'd find they're over in the Euler category quite often. So this is a sort of little algorithm here, which I may not have time to go through completely. I'm almost out of time, I see. But it gives you a set of steps. We've got to know the force and the length of the column. Got to find the A, the I, and the K. Find the slenderness ratio. look at the boundary conditions, see if we want to fudge the L to be something different than the actual L from that table. Pick a material, most often steel. The stiffer the better for a column, so I don't want to make a column out of an unstiff material, so most you'll find a steel. Steel is also a very cost-efficient material. It's not that expensive. On a cost per strength or a cost per stiffness basis, it wins hands down most days. Find out what the magic number of SR is at that point D, where I transition from one regime to the other, and see which side am I on. Am I on the left or the right? So I do that calculation, and depending on how that comes out, I either use one or the other of the two formulas. And I find out what my critical load is. Now that critical load is the load at which it's going to break. Okay? So I've got to back off from that by some comfort factor, which I recommend should be at least 2. Let me say a word about safety factor. Every time I bring it up, I want to reinforce the idea. It's an indication of your uncertainty. If I knew perfectly well what my material strength was, I knew exactly what my loads were, I could afford to have a very small safety factor, because I'm pretty confident of my numbers. But most of the time I have neither of those things known very well. For one thing, I may assume one load and the user doubles it. What's the load on a woods bike? I'm designing a woods bike, motorcycle, to go in the woods. People jump them, don't they? You see pictures of them going through the air, turning upside down, right? They got to come down. They're going to hit. What's the load when it hits? Depends on a whole host of factors, right? So I assume a certain height, certain weight of rider, and so forth. Along comes this little pint-sized kid, and he goes twice as high as the other guy. I can't control that. So there's a lot of uncertainty in the whole system, okay? Uncertainty of loading, uncertainty of what the real strength of that piece of steel is I just bought from the store. The book says it should be 45,000 psi. I test it, I find it's only 42. So there's uncertainty everywhere. So seldom do we know our information well enough in machine design to use less than about 2. That's what I shoot for. Now, how many of you have flown an airplane lately? Any idea what the safety factor is for a commercial airliner at Boeing? Not quite 1.1. That's military. The military pilot wears a parachute, does he not? Military aircraft safety factor is 1.1. Commercial airliners, 1.2 to 1.3. Makes you warm all over, doesn't it? I'll tell you, being an engineer is a very distinct disadvantage when you fly. You look out at that wing, and you're picturing the stresses in the root. I hope I get home. So, it depends on the circumstances. A bridge, big safety factor. Some safety factors are legislated by law. That's redundant, isn't it? And elevators, good example. I can't remember the number, but it's big. So the state says you design an elevator, you must have a safety factor of like 4 or 6 or some number like that. Don't quote me because I don't remember the number. But it's big compared to what we typically do for machinery. Because what happens if that cable breaks on the 15th floor and there's 10 people in the elevator? Curtains. You know, they're in a puddle at the bottom. So when life is at stake, you need a good safety factor. What about airplanes? All right, I'm going to stop here because I'm out of time. You can look this over and get a better sense of how to do that column problem.